We present a model compression framework for 3D facial animation. Our hybrid knowledge distillation method compresses a large, high-quality model into lightweight models that run in real time and on-device. Despite their reduced size and latency, these models retain much of the original performance, including robust generalization across speakers, audio quality, and languages. Here, you can see animations generated by models of different sizes and latencies.
To be or not to be, that is the question, whether 'tis nobler in the mind to suffer the slings and arrows. What? No, Hamlet speaking.
One thinks one hears hydras talking.
Philip therefore read diligently in the Astor Library, planned literary works that should compel attention, and nursed his genius.
Modern machine learning models designed for 3D facial animation often employ large-scale, pre-trained speech encoders to improve quality and robustness. This means that one needs a dedicated machine to run inference, which makes these models mostly suitable for offline processing. We are interested in real-time applications in computer games, such as virtual avatars and animating a player's speech on their character. These applications require small and fast models that produce high-quality animations. In this work, we show how to compress large-scale facial animation models into real-time and on-device models using a two-stage distillation framework. Our method begins by distilling the original model into a smaller model with a completely different architecture. This is stage 1. In stage 2, we use both the original and the small model as teachers to train two final lightweight variants, one for on-device use and one for real-time applications. They both share similar architectures with the small model. To explain how we compress large-scale facial animation models, we first introduce the model that we want to distill, voice-to-face. Voice-to-face is a machine learning tool that generates lip-sync animation directly from recorded speech.
Mark your targets and don't miss. I spot them, you take the shot. Ready to deploy.
Let us first look at its original architecture. The original voice-to-face model takes raw speech as input and generates rig animation frame by frame. It has three core components: a pre-trained Hubert speech encoder, a mesh generator that maps audio features to 3D facial meshes, and a mesh-to-rig module that converts meshes into animation rig parameters. The model processes full-length audio, typically 10 to 20 seconds, and produces high-quality, lip-synced facial animation at 30 frames per second. It has approximately 1 billion parameters and requires 4 to 5 gigabytes of memory to generate animation. In contrast, our small voice-to-face model processes only a 512 millisecond audio window using 256 milliseconds of past and future context. It predicts rig parameters directly, frame by frame. With a fully convolutional architecture, it's optimized for speed and efficiency, enabling real-time animation with a small computational footprint. It contains just 3 million parameters and requires only 21 megabytes of memory per frame. We train the small model using knowledge distillation. First, we use 960 hours LibreSpeech dataset to generate pseudo-labels with the original voice-to-face model. Then we supervise the small model using both a reconstruction loss and a velocity loss to ensure temporal smoothness in facial motion. We refer to this process as heterogeneous knowledge distillation due to the significant architectural gap between the teacher and the student models. Now, let's take a look at the small model running in real time. This video presents example animations from our real-time, low-resource spatial animation models trained with varying memory and delay configurations. The current demo is operating in real time, where buffered audio is converted into rig parameters rendered at 30 frames per second. The model showcased in this real-time demo has a delay of 256 milliseconds and uses 21 megabytes of memory per frame. The latency of the entire system in this demo is approximately 350 milliseconds. This includes everything from speech to rendering. Building on the small voice-to-face model, we designed two variants optimized for on-device and real-time use: For the on-device version, we reduced the number of convolutional channels by 75%, resulting in a tiny model with just 0.2 million parameters and a 3.4 megabyte per frame memory footprint. Our real-time design shifts the input window further into the past, keeping its total length unchanged. This simple adjustment reduces the output latency to just 64 milliseconds, only 25% of the original 256 millisecond delay. We introduce a second-stage training framework tailored for on-device and real-time models. In this stage, pseudo-labels continue to guide training, while a frozen small voice-to-face model, trained in the previous stage, serves as a second teacher, leveraging its architectural similarity and strong performance. Feature loss is added to promote faster convergence and improve the overall quality of the two variants. We refer to this framework as hybrid knowledge distillation, as it combines heterogeneous distillation from the large teacher model with homogeneous distillation from a smaller teacher model. To demonstrate the generalization capability of our lightweight models, we present here two evaluation scenarios. First, we test generalization to different languages. We compare four models: the small teacher model from stage 1, an MFCC baseline model also using a convolutional architecture, but with MFCC input instead of raw speech, our on-device student model, and our real-time model. We include speech samples in German, Spanish, Japanese, Cantonese, and Mandarin.
Die Nutzenfunktion hat die üblichen neoklassischen Annahmen.
Juhu! Und baute es zu einem der bedeutendsten Stahlbauunternehmen Deutschlands aus.
Hay muchas formas de cajas japonesas y de diferentes patrones.
Desafortunadamente, Garth es un mal perdedor y secuestra a Abbey.
主人はあまり口をきかぬ人と見えた。
一向に見当がつかなくなっていました。
归居廣州養母。
目前担任中华台北男子篮球代表队总教练。
Second, we evaluate robustness to audio quality by downsampling the input from 16 kHz to 8 kHz, simulating low-fidelity audio. In this case, the performance gap between our models and the MFCC baseline becomes even more pronounced.
To be or not to be, that is the question, whether 'tis nobler in the mind to suffer the slings and arrows. What? No, Hamlet speaking.
One thinks one hears hydras talking.
Philip therefore read diligently in the Astor Library, planned literary works that should compel attention, and nursed his genius.
To illustrate latency differences, we compare two models, one with 256 milliseconds and one with 64 milliseconds latency. Both use the same input window, but the 64 millisecond model predicts each frame approximately 192 milliseconds earlier.
To be or not to be, that is the question, whether 'tis nobler in the mind to suffer the slings and arrows. What? No, Hamlet speaking.
One thinks one hears hydras talking.
Philip therefore read diligently in the Astor Library, planned literary works that should compel attention, and nursed his genius.
Finally, we demonstrate the generalization of our framework by using a recent model, CodeTalker, as the teacher instead of voice-to-face. CodeTalker predicts mesh data directly, so we adapt our student model's output layer accordingly. The result shown here is from stage 1 of our distillation pipeline, which forms the foundation for our two-stage approach.
To be or not to be, that is the question, whether 'tis nobler in the mind to suffer the slings and arrows. What? No, Hamlet speaking.
One thinks one hears hydras talking.
Philip therefore read diligently in the Astor Library, planned literary works that should compel attention, and nursed his genius.